Welcome to this video. We're underway in the North Atlantic Ocean on our way from Rockland, Maine to St. Croix in the Caribbean aboard the 134-foot tall ship, the Corwith Cramer, which is with Sea Education Association. I often sail with Sea Education Association. They're a great organization for study abroad and all kinds of oceanography and maritime policy type programs for your youngsters there. But anyway, we're bringing the ship down to the Caribbean, and we've got kind of a flat, calm day. We're motor sailing, so we figured it would be a good day to do some celestial sight video recording. And in this video, we're going to prepare for and then execute evening stars. We're going to calculate the time to twilight, so when we know when to go up on deck. Then we're going to shoot a bunch of objects. We're probably going to record 2 objects just to keep the length of the video reasonable. We'll reduce those into our position to get our position from evening stars. All right, so let's get started. So we're getting towards sunset. Clearly twilight is coming. But for tonight, the mission is to get ready for evening stars. So we'll calculate the time of astronomical twilight and civil twilight, and then we'll be out here observing the stars this evening. Okay, so the first task is kind of calculating the time of twilight, and that sounds easier than it might be. There's actually a lot of different twilights. So for instance, there's civil twilight, nautical twilight, astronomical twilight. Civil twilight is when the sun is 6 degrees below the horizon. Nautical twilight is 12 degrees below the horizon, and astronomical is 18 degrees. So they get darker and darker for sunset or lighter and lighter for sunrise. Traditionally, nautical twilight is when you go out and observe stars. I found that I like civil twilight better. Like, I guess I have really good eyesight or something, but somewhere in there you can do it. So the way to calculate it, we're going to use the Nautical Almanac, and we're in 2022 for this one. So I'm going to go to today's date, which is November 13th for us. And right down here in the right-hand corner, there's times of sunset, sunrise, twilight for civil and nautical. So we're going to be focusing on the civil twilight column here. So I'll just bring that up so you can see it a little bit better in the camera, the civil twilight column. And really the way that this works is this gives you civil twilight times or nautical twilight or sunset times. It works the exact same way for standard latitudes and standard longitudes. So for the standard latitudes, they're listed. So 0, 10, 20, 30, 35, 40, etc. Note that they are different values as the table goes up. And the Earth is round, if you believe in that sort of thing. So it's not like a linear representation of these things. So what you want to do is you want to choose the latitude that is less than your latitude. So my ship is at latitude 23. We're going to choose 20. So I note the time of civil twilight for this latitude is 1744. So I'm just going to write down 1744 is my latitude time. So our latitude time is 1744, but remember that our latitude was not 20, our latitude is 23. And so we need to take a little bit of data from here, and we're going to use a table to convert that. So the tabular interval, the interval between consecutive latitudes, between 20 and 30 here, is 10 degrees. Likewise, the difference between our time of 1744 at 20 and 1730 at 30 is 14 minutes. So we're going to need that information. So I'm going to write down the tabular interval is 10 and the time was 14 minutes. If I go to the back of the Nautical Almanac, there's a table, table 1 for latitude. You can do this mathematically, but the tabular interval is 10 and we are 3 degrees along that interval between 20 and 30. The difference between times for consecutive latitudes is 14 minutes. The closest value is 15, so our value here is going to be 4 minutes. 4 minutes. Well, what do we do with that 4 minutes? If we look back at the tables, we can see that 1744 was the value for 20 degrees and it's less for 30. So we're somewhere between 20 and 30, so we need to subtract those 4 minutes. So our latitude corrected time is going to be 40 minutes latitude. All right, and I mentioned standard latitudes and standard longitudes. The standard latitudes are easy because they're written into the Nautical Almanac. The standard longitudes are a little different. So if you assume the Earth, and there's Greenwich, England at 0 degrees west, the prime meridian, every 15 degrees out from there is a standard longitude. So 15 west, 30 west, 45 west, 60 west, and 75 west. And we're in the North Atlantic Ocean, right? So the same thing applies to the Eastern Hemisphere, but we're somewhere over here. We're at 66 degrees west, 66 and 39 minutes actually. So we're somewhere like out here. So what is the difference going on here? Well, these times, these 1740 that we calculated is going to apply here and here and here and here and here, but not in the middle. So every time zone is 15 degrees wide or 1 hour long. So if we were magically transported over here, the sunset's going to be at 1740, or the twilight's going to be at 1740, but our watch is going to be only 3 hours from Greenwich instead of 4 hours from Greenwich. So that's neither here nor there. What we need to do is we need to find the difference between our position and the standard meridian from which it originates. And luckily, if we know that each of these is 15 degrees wide, we could do the same kind of, we could do this by math, but the easiest way to do it is to use the conversion of arc to time table. And the conversion of arc to time does that. It converts arc, or degrees, to time. And so if we go, we're looking at a difference of 6 degrees here, 6 degrees and 39 minutes for our DR position. So 6 degrees is equal to 24 minutes. 6 degrees equals 24 minutes. And then over here, we can see that there are 39 minutes of arc, which is equal to 2 minutes and 36 seconds of time. We're going to round that to 3 minutes. So we need to adjust this by 27 minutes. Things happen earlier in the east and later in the west. So if civil twilight is here, 1740 at 60 degrees west, we need to add 27 minutes to it. So that gets us to 18 hours and 07 minutes. So that's the time of civil twilight at my position, my latitude of 23 degrees north and my longitude of 66 degrees 39 minutes. So to recap that process, I'm going to look in the Nautical Almanac for the standard time of sunrise or sunset or civil twilight. In this case, it was 1744. I adjusted it by 4 minutes because I was a little north of the standard latitude. Then I adjusted it by 27 minutes because I was a little west of the standard longitude. And that process is going to work well for sunrise, sunset, local apparent noon, whatever you're doing. So 1807, that's the time we need to go out and be ready to observe stars. That's civil twilight. Anywhere between there and nautical twilight will be the best time to observe. So let's go do it. Hello there. It is evening star time as we calculated earlier. I've got my sextant. We've got some stars and planets coming out. So we're going to shoot a couple of things tonight. We'll record them and then we'll do the reductions down in the chart house. I've got my friend Nate here, the chief engineer and also chief mate. He's quite talented. And he's going to record for me. So he's got a watch and a notebook so we can kind of record things down. And if you want to shine your flashlight on this, we'll make sure our sextant is set to 0. And then we're fortunate to have Jupiter up in the sky, so that's a nice one to start with, unambiguous. So I'm just gonna look at Jupiter, focus my sextant a bit, and then I'm gonna bring that down to the horizon. And on a ship like ours that's moving, only 6 or 7 knots, we don't need to take into account the time between sightings that we have. So when I say mark, Nate, you just note the time, write it down, and then I'll record the reading after that. All right, Jupiter, mark. So Nate's writing down the time. And then for the sight height, we got, oops, sorry, I'll steal that one. It's okay. 44 degrees, 50.2 minutes.
Got it.
All right, so let's go after Polaris if we can find it, just for the unique factor. Polaris is unique in the way that it's reduced. It's a much easier reduction. The challenge tonight, Polaris by itself is a very relatively dim star compared to all the others, so I wouldn't normally choose it, but it is helpful to show the different types of reductions. Also, there's some cloud on the horizon, so I'm not quite sure if I get the cloud or the horizon, but it's going to be close enough, I guess will be the issue there. So, all right, so we'll take the measurement here. 2-3 degrees, which is good because that's approximately our latitude, so that's nice. in 4.2 minutes.
All right, 23:04.2.
All right, so we've got evening stars. We're gonna reduce these and then it's time for bed. Okay, so we're down in the chart house. We've written down our observations. So we observed Jupiter at local time 18:17 and 32 seconds. We observed Polaris at 18:26:03. These were the heights of the sextant that we observed them at. And now it's time to kind of reduce these to calculate our position. Normally I would do more stars, but these are two interesting ones. One's a planet, one is a star, and this star is reduced in a unique way. So this is a great demonstration of how to get a position with two objects relatively quickly. First things first, there was some watch error. I was 20 seconds slow on my watch. So I was slow 20 seconds. So I need to adjust each of these. And so that's going to make this 18, 17, and not 32, but 12. While I'm at it, we were observing a time zone of +4 from GMT. So we need to adjust this hours by 4 hours. We were west of GMT. So if it's 1800 at me, that's 19, 20, 21, 2200 for GMT, which is what the books are calculated for. So we're going to make these adjustments. It's 22, 17, 12 for our actual time for Jupiter. And then it was 22, 25, 43 to account for those 20 seconds that we were kind of slow for each of these. The other thing we need to do is adjust our sextant heights. We read the value of the sextant at 4450.2. Well, there's a couple of things we need to account for. The first thing we need to account for is our dip. Our dip is our height of eye. Our height of eye is on our ship, it's -3.4 for all sites, but we'll show you where to find that. If we go to the front of the Nautical Almanac, there's a dip table, and this corresponds to your height of eye. So for us, our height of eye is around 12 feet. So the height correction, the dip correction is -3.4 for all of our sites. So I'm going to take away 3.4 for each of these. So -3.4, -3.4. And that gets us to 44 degrees, 46.8 for this one, and 23 degrees, 00.8 for this one. The other thing we need to account for in this sighting is some of the apparent altitude corrections. These are also noted kind of in the front of the Nautical Almanac, these apparent altitude corrections. And before I go too farther, the sextant had no errors in it. So sometimes you need to account for the sextant error itself, the index error. Ours are perfectly adjusted, thank you very much. So we don't have to make corrections for there. So I'm going to look over here for any planet corrections. There's no Jupiter corrections, which is good. So everything is going to come out of this column. I'm going to take my apparent altitude and I'm going to pull the correction from it. So the apparent altitude of Jupiter is 44.46. So I'm going to go down to 44.46. There's nothing there, but I see that in between these two values, there's a -1.0 correction. So that makes this 44 degrees, 45.8 minutes. That's our HO, our height observed. So I'm going to do the same thing for Polaris. The apparent altitude was 2300.8. So 2300.8, I see it's a -2.3 correction. These are always challenging when you go, below 60 there. So 60.8 is equivalent to 60.8 minus 2.3 gets me to 58.5, 22 degrees. So I made that change there. So that's my HO for Polaris, height observed. That's good. So here's a look at the big picture, just of what we've done so far. This is kind of step one of our process, our 5-step process. You can refer to other videos if you are unfamiliar with my 5-step process, but we've got the shooting and the observing and the correction of the objects. The next thing to do is kind of find where that object was in the sky at the time that we shot it. And so I'm going to use the Nautical Almanac again for that. I'm going to find the GHA and the declination of these objects. The GHA is the Greenwich hour angle, kind of how far west of Greenwich it is, and the declination is the distance north or south of the equator for that spot directly beneath the object. I need to find that spot so I can plot it onto a chart. All right, so we go to today's date, which is November 13th, and there's all kinds of information here On the right side is the sun and the moon and the twilights and stuff. On the left side is the stars and the planets. And so for the first one, Jupiter, I'm just going to go to 13 November for our date, and I'm going to look at a time of 2200 hours. So I see that Jupiter's GHA is 2320.3, and its declination is given here at 147.2. So I'm just going to write that down. GHA is equal to 23 degrees 20.8 minutes west of Greenwich, and the declination is south 1 degree 47.2 minutes. All right, we'll do the same thing for Polaris while we're here. However, Polaris is a little different. We need to use Aries for this one. So the GHA of Aries on the 13th at 2200 is 2259.7. 22 degrees 59.7. And we don't care about declination for Polaris. So we can zoom in there and get our situation going for where we're at. Of note, let's look at the declination first. From hour to hour, the declination of Jupiter does not change significantly. So from 2200 to 2300, it changes by decimal 1 minutes there. So we need to make no change to our declination. However, comma, the GHA does change significantly. You can see that's a big change from hour to hour. So what we can do is we can use the tables in the back, the increments and corrections. And I'm going to go to 17 minutes and 12 seconds and pull out a correction. 17 minutes and 12 seconds, the sun and the planets are going to move by 4 degrees and 18 minutes. 4 degrees and 18 minutes. Always west. If you are thoroughly proficient in celestial navigation, you probably shouldn't be watching this video, but you'll notice there is a little V correction for Jupiter as well. We're going to pass on that one. It's a very minor correction. It just ends up taking up time and kind of confusing people, so we're going to just pass on that little correction. It's insignificant enough for celestial navigation purposes. So we need to add these up, so we get 0.88327 degrees. So that's the actual GHA, and that's the actual declination for Jupiter, which is good. So the next step in the process, that's kind of step 2. So step 1 was shooting and correcting. Step 2 is finding the object. Step 3 is kind of building a celestial triangle. In the case of Jupiter, for Polaris, we don't have to do as much for that. But what we want to do is note that our dead reckoning longitude was 66 degrees and 39.4 minutes west. Our DR latitude, our approximate position, was 22 degrees 56.4 north. So this is kind of our estimated position. We pulled it off the GPS in reality, so no big deal there. But yeah, we need that information for this step. And so if my GHA of Jupiter is 2738.8, the way that I'm going to construct my navigational triangle is I'm going to do the formula LHA equals GHA minus longitude. So this formula LHA equals GHA minus longitude is designed to help us get our LHA. If we were to draw all this out, if here is Greenwich, here is our ship, and here is the star or planet, this is longitude. This is GHA. And so the difference, what we're looking for, this difference here, LHA, is GHA minus longitude. So if my longitude is 66 and my GHA is 27, I can't quite do that math without adding 360 degrees. So I'm going to take the GHA of 27, I'm going to add 360 degrees, and I'm going to get 387, 38.8. My longitude is 66 degrees, but I want a whole number of LHA. So I'm going to subtract, instead of 39.4, I'm going to subtract 38.8. And I'm going to note that as my longitude. So that way these go away, and 387 minus 66, It's 321. While I'm here, the declination is south 1 degree and some change, which we'll account for later. And our latitude is 23 north to the nearest whole latitude. These are the three things that I'm going to need to go into HO229. All right, how about for Polaris? Well, do we need to do all of this? Sort of, not everything. But for Polaris, we need to get the LHA of Aries. And so instead of the doing it for Jupiter, we're doing it for Aries. Not even for Polaris, just for Aries. So the GHA of Aries is 2259.7. Again, our longitude is 6639.4. So I'm going to take 22 plus 360 to get 382 minus 66. And my LHA is going to be 316. Because my assumed longitude, I'm going to just assume it's 59.7. Everything goes away. It's no big deal. But for the purposes of a Polaris site, all I need to do is get a whole number of LHA really quickly. And that part's done. I do also need to note, I guess, our latitude was 23 degrees north, roughly. And yeah, that's pretty much it. Okay, so here's a look at the whole process so far. Step 1 was to take the observation and then correct it. Step 2 was to find the objects, GHA and declination. Step 3 was to build a triangle, a celestial triangle, finding LHA, declination, and latitude so that we can use HO229. So we're going to move on to the next step, and that is kind of solving this triangle using HO229. So when I go into HO229, I need to look up certain information. And so I need to know, if I open to a random page, I need to know the latitude, the LHA, and the declination. So let's go after Jupiter in this case. And so its LHA was 321. Going the wrong way. So here's LHA 321. Latitude is the same name as declination or contrary? Well, it's contrary. The latitude was 23 degrees north. The declination was 1 degree south. So I'm going to use this page right here. I know this is tricky to see on camera. So we'll zoom in as much as we can. We'll focus. And my latitude is 23. My LHA is 321. You'll have to trust me on that. My declination is 1. So my height computed is 4506.5. 4506.5. My little d number is negative 34.6. And my z is 116.9. So what do those all mean? Well, honestly, it doesn't matter. We need to write them down now, but before we forget. Okay, so we've written down the stuff from HO229. We've got our HC, which is the computed height of the object if you were standing at the assumed position, which we're not. D is the correction factor for this little bit of declination that we forgot to account for, this 47.2. And then Z is the azimuth, what direction that object was on a compass. So let's deal with Z first. It's quite easy. If you're in the northern latitude and your LHA is greater than 180, which it is in this case, then the Zn is equal to Z. So no correction is needed. This is the direction from our object, from our position to the object up in space. This D correction accounts, like I said, for the 47.2 minutes of declination that we didn't look up before. So the easiest way to do this, I find, is to go 34.6, that number, times 47.2, divide it all by 60, and you get 27 corrections. So you need to subtract 27.2 from this HC value up here. And if you do that, you get 44 degrees, 39.3. That's the final HC value. All right. So if we compare that 44, 39.3 to this observed 44, 45.8, there's a difference. The difference is going to be 6.5 minutes. And is it, the way that we need to calculate this, if the computed value is greater, it's away from the AP. And if the HO is more, it's towards. So it's towards. So again, you can check out some other videos if you want a deep dive in that process. So we've got everything we need for Jupiter. How about for Polaris? So for Polaris, we can just go into the Polaris tables and pull out all of our corrections to get our latitude, which is quite handy. So the way that we're going to do this is we go to the LHA of Aries, 316, so 310 to 319, here's the 6. So our correction is going to be 58.4. Then we stay in the same column. Our latitude was 23, so our correction is 0.4. We stay in the same column. Our month was November, so our correction is 1.0. And then they give you the formula right here. Latitude is apparent altitude minus 1 plus those 3 corrections that we just noted. So if we go into our page, here's our apparent altitude, minus 1 plus the 3 corrections. And if we kind of do those corrections, we're going to get 22 degrees, 58.3 for our latitude, which is great. That's our designated latitude. You don't need to do anything else with the Nautical Almanac from there. We've got our latitude, and we've got another cross site that we can use to kind of check our position. So let's plot out this on a universal plotting sheet. So usually we're going to construct a universal plotting sheet if we're like in the middle of the ocean like we are in this example. And so I'm going to use magic markers or Sharpies just to make it a little more obvious. I wouldn't recommend doing that in real life, right? You're going to lose a little bit of accuracy. But the way that we're going to construct these universal plotting sheets, and I do have a video, specifically about these if you're interested in more. But you need to pick a central latitude. So we're going to pick a latitude of 23 degrees north. And then these become the next latitude. Of note, you can kind of zoom in or zoom out on your universal plotting sheets by like dividing these intervals in place, but we're just going to leave it alone. It's going to be good enough for open ocean celestial navigation. So I've set my latitude scales, which is good. Then I pick the mid-latitude and I go down to this little kind of interpolation scale, rather, and I kind of set up myself on 23 degrees for the mid-latitude. And that represents 1 degree of longitude. So if I go from 0 to 10 on one side and 50 on the other, that represents 1 degree of longitude. There are some shortcuts you can take if you're in kind of like the middle latitudes, but we're going to do it this way here. So that's 1 degree of longitude, rather, 1 degree of longitude. Sorry if I said latitude earlier. So we'll mark those off. And now we can kind of connect the dots. I want to make ourselves parallel here, or perpendicular rather. And we've got our universal plotting sheet kind of set up. We can choose whatever longitude we want. We can choose the latitude based on kind of the mid-latitude. So I'm going to choose 66 degrees west. That makes this 65 west and this 67 degrees west. So we've got our kind of zoomed in chart for our celestial navigation process. Our dead reckoning position, I'm not going to include because we want to do this as if we were doing a celestial site. So the first thing we can do is we can plot out our latitude from Polaris. Quite easy to do that. We said the latitude was 2258.3. So here's 2250, 55, 56, 57, 58.3. So we'll kind of do that, make ourselves perpendicular here. I'm going to leave a little bit of room to account for the Sharpie. So that's our latitude from Polaris. Pretty cool, pretty easy to do that site. The next thing we did is we shot Jupiter. And so we said in the process of shooting Jupiter, we kind of said that the latitude, our DR latitude was 2256.4, and we chose a latitude of 23. Likewise, when we calculated our LHA, we calculated we assumed an assumed position longitude of 6638.8. So I need to plot both of those onto this chart as well to get the assumed position. So the latitude was 23, that's great. The longitude was 6638.8. So I'm going to go kind of down here, go to 30 and 8.8. So that makes that the assumed position for Jupiter, which you might not be able to see, so we'll make it red. So I'm going to label that AP Jupiter. AP Jupiter. We calculated that it had a azimuth of 116.9. So if I take my triangle and I set it up to 116.9, using that inner ring there, 116.9, which is great. And then I take my other triangle and I move this over to the assumed position of Jupiter. I can plot that out. We were towards Jupiter. How far were we towards Jupiter? 6.6 nautical miles. So there's 6.6 miles. That's the mark. And if I make a perpendicular mark to my azimuth, that's going to be Jupiter. So where this Polaris line in purple and this Jupiter line in red cross is our fix. This yellow line is just for constructing the position. And if you remember back from the beginning of the video where we showed the dead reckoning position, it was very close to that, which is good. So this looks like a good celestial sighting from there. So again, in reality, I would probably use 3 objects if I was depending on this for my position, but for an exercise and you know, kind of like a practice for celestial navigation, 2 objects is perfectly good for teaching, and we found ourselves in the correct position, which is always a nice feeling. All right, good luck, sail safe.